All right, so we're going to use our trigonometric identities that we previously discussed to try and do a number of things, from evaluating functions to simplifying different trigonometric expressions. So we're going to start with these problems here. And I'm actually going to start with number 2. Hopefully, this helps us understand a little better before we try some of the other ones. So let's start with number 2. So looking at this, we're going to say that the sine of x is equal to 1/2. And we're also given this bit of information that the cosine of x is going to be positive. It's greater than 0. So we already have a sense of what the sine of x is. We can even draw a triangle to give us a sense here, right? We can go ahead and say, all right, if the sine of my angle x is 1/2, meaning my opposite side is 1, my hypotenuse is 2, we know that means our adjacent side is 3, which we can just get using the Pythagorean Theorem. And the fact that cosine of x is greater than 0 tells us that we are in quadrant 1, okay? So from here, we can say a couple of things. We can say sine x is equal to 1/2, which we already know. The cosine of x is equal to √3/2. The tangent of x is equal to 1/√3, which we can then rationalize to √3/3. Cosecant of x is equal to just the reciprocal of sine. Secant of x is going to be equal to 2√3/3. And the cotangent of x is equal to √3. Now you might be looking at this and saying, wait, we didn't really need many of the identities to do this, right? Because these are all problems that you should have been able to do previously. Well, the only reason we're using identities right now is these here. We're just using the reciprocal identities. It's just one example of using some identities to evaluate some trig functions. Okay, but let's try some other ones. Okay, let's look at number 3 right now. So for number 3, we're told that the secant of u is equal to -3/2, which we can then use the reciprocal identity to say that the cosine of u is equal to -2/3. Okay. Now, from there, we're told that the tangent of u is greater than 0. Now, the reason why this is important is because the cosine of u being negative tells us that we could be either in quadrant 2 or quadrant 3, right? That's what we're not sure about. Is it quadrant 2 or quadrant 3? But the fact that we're told that the tangent of u is positive, remember, all students take calculus. If tangent of u is greater than 0, then that tells me that we have to be in quadrant 3. So we can draw our triangle there. Okay, so looking at this here, we're going to say that our adjacent side is equal to -2. Our hypotenuse is 3. And using the Pythagorean Theorem, which we can just kind of briefly do right here, we could say -2 squared plus y squared is equal to 3 squared. Y would just be equal to √5, plus or minus √5, that is. Well, the fact that we're looking at a triangle or an angle that lies in quadrant 3, since we're in quadrant 3, that tells us that our y value has to be negative. Okay, so using this information here, we can continue to evaluate the rest of those functions. We can say something like cosine of u is equal to -2/3. If I needed to do something like sine, I can say this. Tangent of u would be equal to √5/2, which, by the way, u would be something like this. This would be my angle u. Cosecant of u would be equal to -3√5/5. And the cotangent of u would be equal to 2√5/5. Okay? All right. Now let's try something like number 1. Let's go back. So I know the order was a little strange that we went from 2, 3, and now back to 1, but I think 1 actually uses the most number of identities. So a couple of things here. First off, let's start with the fact that we're saying cosecant of -x is equal to -5. Well, what do we know about cosecant of -x? Cosecant of -x is equal to negative cosecant of x. This is because this function is an odd function. Because that is true, we can then say that cosecant of negative x, since it's equal to -5, negative cosecant of x is also going to be equal to -5. So we can write that. Negative cosecant of x is equal to -5, which then allows us to simplify this as the cosecant of x is equal to +5. And now we can look at the fact that cosecant of x is equal to +5, sine is equal to positive √24/5. Therefore, I know that I must be in quadrant 1 because both cosecant and cosine are positive. So I can draw my triangle here. And I could say something like, well, I know that cosine of my angle x is √24/5, which can be simplified, by the way, to, let's see, 2√6. And using the Pythagorean Theorem, that would be 25, we can say it's 25 minus 24. This side would then have to be equal to 1. And you can just fill out the rest of the trig identities on your own, right? So that should be pretty easy to do. Sine of x is equal to 1/5. We already know what cosine is. Secant of x would be equal to 5√6/12 once you've simplified it. Tangent of x is equal to √6/12. Okay. Oh, I forgot about cotangent. Cotangent of x is equal to 2√6. Okay. So that's using a way of using some of these identities to evaluate some trig functions. Now let's start the process of actually simplifying trig functions using some of these identities. So we're not into the full-blown verification step or process yet, but we're just getting comfortable simplifying, reducing, rewriting some trigonometric expressions using some of our identities, okay? So let's look at something like secant of x, cotangent of x to start. This is a pretty basic one. Well, I'm going to start by using my reciprocal identities to write secant of x as 1/cosine of x. Cotangent of x would be written as cosine of x over sine of x. And this clearly we can see that we can simplify here. So that would just be 1/sine x, which we can then just fully reduce down or rewrite as cosecant of x. Okay. Which, by the way, I should point out, for a lot of these, there isn't going to be just one way of doing it. There's more than one way to simplify or reduce. You can use a number of different identities. So go with whatever is logical for you based on your understanding of these identities. Try something like tangent squared theta over secant squared theta. Well, like I said, you're probably looking at this and you're thinking, man, I could use a Pythagorean identity here. I could use my quotient identities. I'm going to start with a quotient identity. I'm going to rewrite tangent squared theta as sine squared theta over cosine squared theta. And I'm dividing all of this by secant squared theta, which is 1/cosine squared theta. Well, this allows me to rewrite this as the following. So I've got a complex fraction right now. So to divide by something means to multiply by its reciprocal, which allows me just to simplify that out. And now I'm left with just sine squared theta. There we go. Okay. All right. Let's go on and try the other two. We got sine x cosine squared x minus sine x. So one common strategy here is to note that we've got a common factor. In this case, it's the sine function. So I can actually factor that out. So sine x, what we're left with is cosine squared x minus 1. And what do we know about cosine squared x minus 1? That should look familiar to you, right? That is actually, if we say sine squared x plus cosine squared x is equal to 1. If I subtract 1 from both sides and move sine squared x over, I've got cosine squared x minus 1 is equal to negative sine squared x. Let me actually just change this color so it doesn't look like we're part of doing the next step here. Okay, so cosine squared x minus 1 is equal to negative sine squared x, which we can then multiply. And now we're left with negative sine cubed x. And that would be a way of simplifying that one. Okay. All right. Let's move on to number 4. So 4, we can't factor anything out just yet because we don't have a common factor at first glance. But what about after we've rewritten some of these trig functions? So secant theta, for example, I can write as 1 over cosine theta minus sine theta over cosine theta times sine theta. And ask yourself here, there's a couple of ways that you could go about doing this now. You may want to factor out 1 over cosine theta now. Another option is to multiply sine theta by sine theta. So we can say 1 minus sine squared theta all over cosine theta, since they have the same denominator. And what does 1 minus sine squared theta equal to? Well, again, using the Pythagorean identity, right? We know that 1 minus sine squared theta is simply equal to cosine squared theta. So we can substitute that in, cosine squared theta over cosine theta, and that just reduces down to cosine theta. There, that is simplified. Okay. All right. So let's just finish it off with these final two, and we'll move on to 512. Okay. So that one here, the fact that I have pi over 2 minus theta probably gives us a good sense that we are dealing with a cofunction identity. So the cofunction of cotangent would be tangent. So this would be tangent of theta, just using a cofunction identity times cosine of theta. Tangent of theta, now we're asking ourselves, how can I simplify this anymore? What can I do? What can I divide out here? Well, tangent of theta is sine of theta over cosine theta times cosine theta. And voila, that allows us to reduce this down to sine theta. Okay. All right, take a look at number 6 now. Number 6 is something that you may want to try on your own first. I'll give it a minute or a few seconds. Start thinking about your game plan here. Do I see anything within my trigonometric expression right now that tells me right away that I might want to try a certain substitution? And if you're looking at that 1 minus sine squared theta, chances are you probably want to use the Pythagorean identity. So sine theta cosine theta over cosine squared theta. And there we go. There's our simplification. So now I'm left with sine theta over cosine theta, and we can even simplify that even further. We've got sine theta over cosine theta. That should be tangent theta. There it is. Okay. All right. So hopefully that gives you a good sense of how we can use our identities to start simplifying, rewriting, and even reduce trigonometric expressions.